In this video, I'm going to go over a couple practice problems from the Unit 3 Section 1 practice about the types of bonds and how to identify them. So in this practice, there are really two different kinds of problems. And the first I have on screen, we're looking at a compound C3H8, which is also propane. And we're going to try to classify what kind of bond is occurring between the elements. So right now we're looking at the elements carbon, C, and hydrogen, H. And we want to figure out if we're combining carbon and hydrogen, what kind of bond will occur between them. So what we have to do is first I'll tell us what elements we got. We'll then look for our electronegativities. It looks like carbon over here has an electronegativity of 2.5. And it looks like hydrogen over here has an electronegativity of 2.1. Now remember, it's not about any individual pull. It's about the difference between the pulls. Is the pull between 2.5 and 2.1, is the pull between carbon and hydrogen great enough to make a difference in how they share the electrons? In this case, the difference between the two is 0.4. And if we consult our scale, we're going to find that 0.4 is pretty small. We have a covalent bond because that difference is less than or equal to 0.4. Essentially, this is showing that these atoms will share their electrons pretty much equally. We call this a covalent bond. On the next slide, we have the same thing, except we're looking at barium chloride now. We'll get our elements set up. I'll find barium right here, has an electronegativity of 0.9. Chlorine over here on the right has an electronegativity of 3.0. And when we calculate the difference, remember, you would notice that we might expect this to be negative, but in reality, it's not about negative or positive, it's just the difference in the pull. So in reality, we're just going to look at it being a difference of 2.1. Consulting our scale, we'll see that 2.1 corresponds to an ionic bond. Essentially, chlorine is pulling so much harder than barium, comparing their electronegativities. Chlorine's pulling so much harder than barium that it will take barium's electrons, therefore making an ionic bond, where electrons are taken from barium and given to chlorine. Now in this last part, we're going to go through one of the more difficult problems, which is labeling all of the bonds in a molecule as either covalent, polar covalent, or ionic. Notice that in this molecule, we have propanol on screen. We have 4 different types of bonds. Some are carbon-to-carbon bonds, as shown here and here. Some are carbon-to-hydrogen bonds. We have a whole bunch of them. They're all over the place. Carbon to hydrogen, okay? Our third type of bond is carbon to oxygen, which is one of those here. And our fourth is oxygen to hydrogen, and we can see that over here on the right side. We want to label all of these as either covalent, polar covalent, or ionic to see how this molecule looks three-dimensionally. So I have a big table here. We'll be filling it out step by step, but it's the same basic process to start. We have our 3 elements set up here. Carbon, we actually have some of these from before. Carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. And oxygen has an electronegativity of 3.5. So I'll put those in my table. Now I have each of the 4 bonds over here on the left, and we're going to find their electronegativity differences. For carbon to carbon, we have 2.5 minus 2.5. Gives us a difference of 0. This should make sense because each carbon will pull the exact same amount, so there's no difference. And no difference puts us at a covalent bond. 0 is indeed less than or equal to 0.4. Carbon to hydrogen, our second example. Carbon has an electronegativity of 2.5 minus hydrogen's electronegativity of 2.1 gives us an overall difference of 0.4. That again puts us just at the edge of this covalent range. It is equal to 0.4, and we go with covalent in that case. Carbon to oxygen, 2.5 minus oxygen's 3.5. Remember, we don't care about negative, so it's just going to be the value, 1.0. And 1.0 puts us right in this polar covalent range, kind of right in the middle. So this is an unequal sharing. I've abbreviated here as polar C. Essentially, oxygen is pulling the electrons away from carbon, but not enough to change what kind of bond it is. It's still covalent, it's just polar. The electrons are closer to the oxygen. And finally, we have oxygen to hydrogen. 3.5 for oxygen minus 2.1 for hydrogen gives us 1.4, so it's a little more polar than our carbon to oxygen, but it still falls in that polar covalent range. It's not enough of a difference to become ionic. Now let's transfer those results to our image. And now as we're looking at the model, let's actually label these bonds. We discovered on the last slide that our bonds have these types. Carbon to carbon is covalent. Carbon to hydrogen is covalent as well. Carbon to oxygen and oxygen to hydrogen are both polar covalent. Now we could do this one of two ways. I could either label the bonds individually, say for carbon to carbon, I could say abbreviating that C as covalent. And if I skip down here to carbon to oxygen, I could again do maybe PC to be polar covalent. But I have a slightly better way. If I create a key with a couple different colors, I can label these bonds as their colors. I can just highlight them. Carbon to carbon, we said it was covalent, so these two spots here, I'll label those as covalent bonds. Our carbon to hydrogen, all 7 of them on this side of the molecule are also covalent. Our carbon to oxygen is polar covalent, and our oxygen to hydrogen is polar covalent as well. And this shows us that our molecule has this very large covalent region and then a small polar covalent region as well. So our molecule has kind of like 2 ends to it, a polar end on the right and a large regular covalent, you can also call this nonpolar region on the left. And that's how we complete the practice for Unit 3, Section 1.